Hi everybody, this is Evergreen Hacker with you. We are at leetcode.com, and as you remember, we were doing weekly contest number 4. We've already done rotate function. Now it's time to do integer replacement. I'll give you a few seconds to read through the description and examples. Okay, so let's look at how many options do we have here. It's 2, and not those 2, but those 2. Let me explain why. So if n is even, then we have no options, 0. We have to divide it by 2. That's it. If n is odd, then we have to either add 1 or remove 1. That's it. Just 2 options. So on the examples, if we have 8, which is a power of 2, then we just have to divide it by 2 3 times until it reaches 1. If it's 7, then we either bump it up to 8, which takes 1 step, and then we know what to do with 8 already, or we downgrade it to 6, and we do a bunch of divide by 2's mixed with minus 1's until we also reach 1. But both of those guys, they take 4 steps, so it doesn't really matter which one wins. So we can do the direct implementation of rules in the task, and I guess it will be enough, but let's try. So we would have to implement a recursion for this case, because we are going to explore the tree of options. And for that, let's create another method here. Whoops, self, which will take 2 arguments. So n will be the number which we will modify. Originally, it takes the same value as this guy, but then it will be either divided by 2 or we will add or remove 1 from it. So we will do those 3 operations. And we will return how many steps did it require for us to reach 1. So let's add the edge case first. If n is 1, or let's also say less than 1, just in case, if someone passes 0 to us, but I guess it's not allowed. Yeah, because it says it's a positive integer. Okay. So we do the following, just return 0, then if n is even, then we return whatever rec returns for smaller n, but for steps plus 1, because we've already done 1 step towards 1, and else we would have to do the minimum. So we just say that we return minimum of self rec n plus 1, steps plus 1, and I guess same stuff but minus 1. Okay, and then we have to call it somehow. So return self rec, and what are we passing there? Our original n and 0. Okay, so this is the draft. Now we have to examine that if we have some bugs here. Probably we do. For that, as you remember, we have to debug it, and we have this powerful debugger which we will use. Oh, actually, let's do this type of comments. And so let's try with 8, because we already know that it has to be this path which wins, and we can try it. So n equals 8 and steps equals 0. So this will be the initial call for rec, and now we have to go through all of those cases. It's bigger than 1, so we go here. It's whoops, so this is the first error. It should be 0 here because we are analyzing the module, which is what's the reminder if we divide by 2, and it should be 0 for even numbers, not 1. So we have to just divide n by 2 and call the same function with steps plus 1. So let's put it here. So we call it with 4. Yeah, actually, let's draw the tree. So 8, 0, this was our initial position, and then 4, 1. This is how we called rec second time. Okay, so now we go here, n is bigger than 1, then it also goes to the same branch as before. So we call it with 2 and 2, because we divided 4 by 2, it becomes 2, and steps plus 1 is 2. And now we go to another call, and we check this guy also doesn't pass, so we end up at the same branch again. And now we call it with 1, 3. So another iteration, now we pass this check actually, and we return 0. Okay, we return 0. This stuff returns 0. This stuff also returns 0, because we are just doing return, nothing else. 0, 0. So 0 is not what we wanted. We wanted to get 3 here. So in order to get 3 here, we had to get 3 also here, and here, and here. But how do we do that? Because this guy has to return 3. And it's exactly the steps that we have. 3, 3. Okay, so we had an issue here. Now we fix that. Let's run it with 7. So we have 7, 0, our initial state. We pass through those two guys and we end up in this branch. So we call 2 recs. The first one will be with 8. And for this, I will not repeat the same stuff. We already know the answer. And then with 6. So what happens with 6? Let's just put 4 here, because we know for 8, 0 we had 3, but for 8, 1 we should have 4, because we start with number of steps 1 already. So for 6, 1, we skip this guy, and then we go into this branch, and we call the rec method with 3. So we skip this guy again, we skip this branch, and we go here. So here we have either, here we have 1, but we should have had 2. So now it should be 3 here, or another option would be to have 4 with the same number 3. And yeah, they should be in different order, because first we check n plus 1 and then we check n minus 1. So then it ends up in this branch, and we call the following iteration with 1, 5. Okay, we reached 5, result will be 5. And here we go straight to 1, 4, and the result will be 4. Okay, so this will be skipped and this will win. So we have 4 as a result. And let's just remove this branch and see what we have here. 6, 3, 2, 1. 6, 3, 2, 1. So that's what we wanted. Okay. So now let's run it. Okay. It works. Now let's submit. Yay! accepted. So that's nice, but let's look at more details. And it says we are here. I don't think it's the best solution ever. The thing is that what we are doing in the brute force case is we do a lot of calculations for unnecessary branches. So we know that we had two branches here, 4, 3, and 2, 3. So 4, 3 gave us 5, and I removed it, I skipped it, but we did those calculations. So this was the waste. Should have we done that, or we could have skipped that? Let's see. Probably we can just go with the -1 always. Why should we go up? Let's look at the binary representation. So 8 is this. Why is that, would you ask? Well, it's quite obvious because 4 is this, and 2 is this, and 1 is 1. So every time we add a 0, it's an equivalent of multiplying by 2 in the binary, because this is in the binary. And we have 3 zeros. It means that we multiplied 1 by 2 3 times, right? But what about this guy? What about 7? So it will be this. And can we do something with that? We can look at how close the number is to the power of 2. So the power of 2 is quite easy to detect. It has zeros here, you know that. But obviously we cannot only have power of 2's. For example, we can have numbers like those ones which are really close to the power of 2, but they have 2 ones here, not just one. And we may also have numbers like that, which have a lot of zeros and some ones. So what should we do with them? I would say that we cannot do anything in case of zeros in the end, or they are called trailing zeros, or zeros and tail. We just have to remove them. But then when we end up having this guy, what do we do with it? Should we go to this, or should we go to this? So this is a question. Like this one would be an equivalent of adding 1, and this one would be an equivalent of removing 1. We can look at what will give us the biggest gain. Like if we have zeros before, like here we had a lot of zeros before 1. So if we had a lot of zeros before, it's more beneficial for us to remove 1 so that we end up having even more zeros, and then we will just remove all of them, and we will end up having very small number. And then in this case, it will not be that beneficial because we would have to remove 1 first, or remove 1 0 first, and then we will end up having 1 again. And then multiple options are here again. So what do we do with it? Do we like shift 1 here if we just add 1, or should we remove 1? So all of them will bring longer path to 1 instead of just dividing by 2. So dividing by 2 is equivalent to shifting to the right in the binary representation. So boom, boom, we divided by 2 times. Boom, boom, 2 more times. Okay, But what happens if we don't have a lot of zeros before 1? Like if we have this case, what do we have to do with it? If we add 1, then we will have this big number. And if we remove 1, we will have this number, which is a bit smaller, but it looks uglier. Why uglier? Well, because it has more ones. And more ones it has, it means more things we have to do with it in order to turn it into 1. Because here, you just do 3 shifts to right so that you remove those zeros. And then you just subtract 1 so that it's 0 again. And you do 3 shifts again and you end up having 1. So it's 7 operations in total. Here, I'm not sure what you will have to do. Remove 1 for sure, but then what next? If you remove 1, you will end up having 0 here, so you have to remove it. We already did 3 operations, and then we do another one. It's 4, 5, 6, 7, 8. So it's at least 1 more than for the previous case. So whatever I'm trying to describe here is not really mathematically correct. It's just an observation, but it looks like we have to add 1 in cases when we have 1 before, and we have to remove 1 in cases when we had 0 before, right? Let's try to implement that and see how it goes, whether we will beat the 52 milliseconds or what was the previous result. Let's see. So we don't change this branch because it's the same as before. We have no options here. But for this guy, for odd cases, we have to look at the previous digit in the binary representation. How do we find the previous digit? Okay, that's quite easy to do. So let's just save this n/2 as a div2 so that we don't do that multiple times. And for div2, we have to, so div2, as you look at it, it's this guy, yeah? Because we just shifted by 1 to right. Or it's this guy, yeah? So we just have to check if it's even or odd. That's it. So if div2 is even, then what we said, we have to remove 1 so that we have more zeros. Return self rec n-1 steps plus 1, and else same stuff, right? But in this case just plus, not minus. Okay, let's try to run it in the debugger. So this case won't change because it only ended up executing this branch, but this case will change. Let's see how. For 7, and as you remember, 7 is 111b, we are looking at the div2, so div2 will be 11b, and it's odd because it has 1 here. So it means that we will go to +1 case. Magically, we end up going to this case and we have 4. So why 4? Because we already know how to calculate this guy. Seems to be okay. Do we have to test on more numbers? Okay, let's try this case, which we didn't try before. So 6. So we'll have 6 zeros, starting point. Let's see where it leads us, because 6 ends up in this range. It's an even number. It means that the next iteration will be with 3, 1, and 3 ends up here. It's an even number. Oh no, we don't know what div2 is, so let's put div2. Div2 is 1, because 3 is 1, 1b, and div2 is just 1, 1 shifted to the right by 1. It means it's just 1. And div2 1 means that it's even, so we end up here. We call third iteration with 4, 2. So 4 ends up here. It means that now we know what to do with it. It will be 2 divided by 2, and we will end up having 4 as a result. But as you can see here, we expected only 3 steps, and we have 4 steps. So something is wrong. So maybe something with div2 being just 1, like 1 is kind of an edge case. As I told you before, it may not even be correct. I don't know, haven't checked. Just used my gut feeling for that. But I still think that it's correct. Let's just try to add this edge case somewhere here. So if div2 is odd or div2 is 1, then we will, instead of increasing it, we will decrease it. And then here we will go with this guy, and we will end up having only 3. Is it correct? 3, 2, 1, 3, 2, 1. Yeah. Let's just verify. Okay, this thing worked. Yay! Accepted. Okay, that's nice. Hey, nice. We moved from this guy to here, and we have 38 milliseconds instead of whatever was before, like 52. It's really good. It's really good. Okay. So what we've learned today is that sometimes you may have some crazy ideas how to optimize the solution, and it may even work. Just have to be careful, really checking all edge cases, including some magic numbers. But it may really optimize your solution and make it much faster. Because here, as you can see, we reduced number of options to just 1. I cannot really advise you to take this crazy optimization approach during your interviews, only if interviewers really ask what can be optimized here, then you can provide such options. But yeah, in my case it worked. I can consider it a luck. Maybe the interviewers will say, yeah, it's good. It's good that you came up with this thing. Or they may also say, well, you didn't prove anything and this doesn't look mathematical at all, so fired. So I don't know. But at least try to implement the brute force case first and then see how it works. Okay, thanks for watching. Please thumbs up to this video, subscribe to my channel, and good luck at your interviews. Bye bye.